Greetings, Physics 221 students. I'm making this video here to help you out on problems 12 and 13 on your Unit 1, Week 1 homework. So let's start with number 12 here. Let's see, an automobile claims that its deluxe sports car will accelerate to 41 meters per second in 8.8 seconds. So what you're given here is a V final of 41 meters per second and a delta T there of 8.8 seconds. Now, this is the one that I printed off. Your numbers may be different, but suffice to say you are given some sort of velocity and some sort of time. Now, you always want to start every one of these with a picture. Get in the habit of doing that right away here. So I'm just going to do a quick little sketch here. Got our automobile. Crummy car, but I'm just going to use this dot to represent the car for the rest of this. Now it starts from rest. The driver gives it gas. The car would accelerate here, and I'm, imagine it's pointing this way. So the motion diagram would look something like this. And again, the velocity of the car would be increasing. Next, draw a velocity graph for the problem. First point, 0, 0. Assuming the car started from rest. Then you have another data point. Now mine's 8.8 and 41. Yours will be something else. I'm just going to call that the delta T. Again, number that you should have. 41, that's going to be up here somewhere. Now, you might ask, how high do I know to put this? This is just a sketch that I'm using to work the problem. I can put that anywhere that I want. But now that I've done so, if I call that 41 meters per second, or basically 40, I have set a scale now. 20 should go about here, 10 maybe here, 50 about here, and so forth. All right, again, you're free to choose a scale when you're just sketching these graphs to help you problem solve. Now, the question here is, how do these things connect? Well, in reality, they probably would connect something like this, because acceleration does start to fall off as the RPMs get higher for a couple of reasons. All right, but that's pretty close to linear. I'm just going to go ahead and assume constant acceleration. Now, these graphs that we're using, we basically have two things to think about, slope and area. Now, the slope is rise over run. That's this over this. Whoops. There we go, over this. And that's going to give you the acceleration of the car. And this area here is going to give you the displacement, the delta x. Now, I know this is a calculus-based class, but there's really, there's no reason to break out integrations and differentiations for most of these problems. And I prefer to just use concepts of area. It's a little more fundamental in nature. And again, I assure you, there'll be problems later on where there's going to be plenty more math. The important thing is recognizing it's this area here. I would just treat this like a triangle, 1/2 base times height to get that area. So that's pretty much number 12. That'll get you through all of these questions, I'm sure. Okay, let's talk about 13. Let's see, a truck covers 35 meters in 8.5 seconds while slowing down to a final speed of 2.4 meters per second. So, we've got a truck. Let's start with oh boy, that's a pretty horrible truck there. Good enough. I'm going to again use this dot to represent the truck. It has some initial velocity that we do not know, but the truck is slowing. So the motion diagram might look something like this for the truck. The final velocity was given in the problem. Now in my example, that was 2.4 meters per second. Yours is probably different. Now it does say that the truck was slowing. And what's the other thing that was given here? Oh, a delta T. There was a delta T given in the problem of 8.5 seconds. Yours likely will be a different number. So start by drawing a sketch of this. Now, the initial velocity we don't know. Just put a dot up here for it and call it v sub I or v sub o. Let's go ahead and put an O on there. Then the truck is slowing down, so 8.5 seconds later, we're going some other velocity, which we know to be lower. Curve's going to look something like this. So our graph is going to look like this right now. Known value, unknown value. Now, so we don't know that initial velocity, and we also don't know the acceleration, do we? That's some number here that I don't think we are given in that problem. So what we're going to do, you have to recognize we have two unknowns in this. We're going to have to write two equations to solve it. Start with this one. I'll do this in blue. The distance that truck covers, whoops, right? That's some sort of delta x, and how is it related to this curve? Area. The area under that velocity curve is equal to displacement, and that's a number given in the problem. In my example, it said that the delta x is 35 meters. Now again, that's my example. Yours is a different number. This is a trapezoid, right? And if you're not familiar finding the area of a trapezoid, go ahead and, I've got videos on it. It's real easy. I can do it real quick. You do left plus right divide by 2 times t. That's going to give you a quick, easy way to get this initial velocity. Once you have the initial velocity, then just go slope of the line between these 2 points will give you the acceleration. So that should be enough on that one. Again, make sure when you're working your homework, draw a nice picture of the problem, include these graphs. If this were a sheet of paper, whoops, didn't like that, but we would want, problem number 1 looking maybe something close to this, and problem number 2 looking something close to this. You don't have to fill the whole sheet, but, don't make the problems little tiny things up in the corner here, okay? I'm getting older, folks, so it's getting harder and harder and tougher for me to see your work. So your homework should always have pictures that describe the problem with all the relevant things listed out. 2 relevant graphs, work, and equations to go with it. So hope that you enjoyed this video. Have a great day.